In this podcast, we're going to talk about what a cyclic hemiacetal is, how it's formed, and why you should care. All right, so let's start by going back and remembering what an acetal versus a hemiacetal is. So we will focus on a carbon. It could be at the end of a chain. It could be in the middle of a chain. A hemiacetal is a carbon with an OR group and an OH group coming off of the same carbon. And an acetal has two OR groups coming off of the same carbon. So that's just a reminder of what those are. In a cyclic hemiacetal, you have a reaction of a compound that has an aldehyde or ketone, and it will react with a hydroxyl group or an OH group on the same molecule. So you have at two ends an aldehyde or ketone and a hydroxyl, and those are going to come together, react to form a cyclic structure. They can contain 5 or 6-membered rings, and I have an example down here of a 5-membered ring and a 6-membered ring. And the cyclic form is more stable than the acyclic form, which is why it tends to do this. So if you have an aldehyde or ketone and a hydroxyl group on the same molecule, most likely that's not as stable as the cyclic form, which is why the reaction happens. And just to help you kind of identify that this is a cyclic hemiacetal, we have a carbon. And this carbon has an OH group and it has an O, and we would consider all this junk an OR group. So this would be considered a hemiacetal. Same thing here, we have a carbon that has both an OH group coming off of it and an OR group coming off of it. So that's how we would identify cyclic hemiacetals. So let's talk specifically about these guys, how these guys form. Here we have 5-hydroxypentanal. So it has an aldehyde and it has an OH group. Essentially, this alcohol group, this hydroxyl group, is going to come around and is going to attack the carbonyl. So just to give you an idea of what this looks like, I'm going to have this wrap around on itself. Okay, so here's carbon 1, 2, 3, 4, 5. All right, so this is carbon 1, 2, 3, 4, 5. Okay, and on here we have our OH group. So the OH is going to attack. And what that's going to do is it's going to form this cyclic structure. So here's our acetal. This is where our acetal is forming. We form a cyclic hemiacetal. Now, we're in Intro to Organic and Biochemistry. This is not something that you have to know exactly how this forms, but it is important to understand that this is similar to how you would form an acyclic hemiacetal. You're going to have this hydroxyl acting as your alcohol, and you're going to have a carbonyl, and it may be an aldehyde at the end of the chain, or it may be a ketone. Either way, it doesn't matter. It reacts with itself, forming this ring structure that contains a hemiacetal in it. All right, so why should you care about cyclic hemiacetals? Cyclic hemiacetals are vitally important in life. Glucose is a great example of a cyclic hemiacetal. Carbohydrates are full of cyclic hemiacetals, whether they are polysaccharides or monosaccharides or disaccharides, they're all full of these cyclic hemiacetals. Just to give you an example, because it is a little hard to visualize these guys at first, look for this is your OR group right here. So imagine this as being O attached to this whole ring. Right here is our carbon. It's attached to an OR group and it's also attached to a hydroxyl. So that's where our cyclic hemiacetal is. And as we go through our carbohydrate chapter, we'll talk a lot more about cyclic hemiacetals, and we'll work on also identifying them in larger structures as well.